right. Hello, everyone. Thank you for listening in. My name is Stephen Pralle, and I am an application engineer here at EAC. And today I'll be talking all about Creo Simulation Live. So our agenda for today, I'll be going over some of the challenges that companies are facing around simulation analysis, talking all about the solution in Creo Simulation Live, talking about some of its capabilities. I'll go ahead and do a short demonstration on how to use CSL and show you guys what value it provides. All right, so before I start listing out some of the challenges around simulation today, I wanted to pose a question for the audience or anyone who is listening in. So up here you can see a high-level product design workflow, and obviously this differentiates between companies and what products they're producing and whatnot. But this is just kind of an overall design workflow for product development. So first we have empathize, define, ideate, prototype, and test. So the question I wanted to ask the audience was, where is simulation analysis used in this design workflow? And the answer to this is it probably depends, right? It depends on the company, what processes they have in place, what type of products they produce, and so on and so forth. So some companies use simulation all the way down in the testing portion of the design workflow. Some use it in the prototype part, and then some don't even use it at all, right? So simulation can be very useful, especially in these beginning parts of the workflow. And I think we can all agree on the more parts of this design workflow that we can use simulation, the better we are off down the line in the design workflow process. So why aren't companies using simulation analysis more throughout the whole design workflow process? Well, traditionally, simulation analysis is very time consuming. Every part about it is time consuming, right? Running the simulation takes a long time. Um, Setting up your part to actually converge and create a solution for the simulation, and then also teaching coworkers how to use simulation, it can also be very time consuming as well. So because of this, engineers are forced to rely on experience. They rely on their experience, their intuition, what they've worked on in the past, and this is very valuable. Don't get me wrong, but when they when they rely only on experience and intuition, sometimes things go missed in the design, and sometimes we find that there are failures later in the workflow that could have been prevented if we use simulation along the way. Another thing is analysis results are often found too late. So if you're not leveraging simulation early on in the design process, you'll find that sometimes analysis results are found too late. We have quality issues when the product hits the market, and so on and so forth. Companies also heavily rely on physical prototypes. And if we're not using simulation before we order these prototypes, there's a lot of time and money that goes wasted when we realize that these prototypes are not performing how they should. So what's the solution to this? Well, it's Creo Simulation Live. So the really cool thing about Creo Simulation Live is that it works directly with Creo Parametric. As you make design changes, you're able to see instantaneously how those design changes affect the performance of your part through simulation. And a little bit of history on Creo Simulation Live. It's actually powered by ANSYS. And if you know anything about simulation, you probably know or have heard of ANSYS before. They've been a leader in engineering simulation for the last probably about 50 years. And what PTC has done is they've partnered with ANSYS with this overreaching goal of removing these barriers for simulation and product development, especially in the early design phases. So some of the capabilities of Creo Simulation Live, first of all, it's a powerful linear solver. So what that means is it rapidly defines and performs linear analysis for parts and assemblies. So you can not only have simple parts, but you can have very complex assemblies that Creo Simulation Live is able to handle. Creo Simulation Live can do structural, thermal, modal, and also fluid analyses as well. And a big important part about CSL is that it's a meshless environment. So like I said before about analysis being time consuming, a lot of that has to do with setting up the part. So making sure the part runs smoothly, defeaturing the part, making sure that you don't have any small holes or small interferences. And the nice thing about CSL is that it does this all automatically in the background. And like I said before, really probably the most important part about CSL is that the results are instantaneous and also interactive. So as soon as you make design changes, within a matter of seconds, you're able to see those results and how they're affecting the performance of your part. And then what you can also do is you can track these results and see, as you're making design changes, how those affect the performance and lay out the history of those changes. All right, so now I'll do a short demonstration on how to use CSL and kind of show you guys what it's all about. All right, so I have Creo Parametric opened right now. I'm using Creo 8. CSL actually runs on any version from 4 to 8. So this part that I have here is actually an assembly, and it's taken from a motorcycle dataset actually. And it's actually the kind of the support bar for the lower hind wheel of a motorcycle. So as we have our part opened, if we want to go to the CSL extension, all we have to do is go up to the top and click on Live Simulation. So now that we've clicked on Live Simulation, you can see that we have some icons up here that have popped up. And also we have our simulation tree here on the left-hand side. So if I open up this structure, you can see that we have predetermined constraints and loads. And for the purpose of time, I've already set these up, but I can kind of go through and explain what these are all about here. So the first one is a displacement constraint. And if I open up the definition, you can kind of see that this displacement constraint is set on these two holes that kind of go through this whole structure. And we have this set up so that it's free to move along the x-axis. And if you take a look at the bottom right-hand side here, you can see our coordinate system. So the x-axis is kind of running along the horizontally across the screen here. And then it's fixed in the y and the z directions. We also have two cylindrical constraints here. So if I open this guy up, you can see that we have a free cylindrical constraint in this socket here, and then as well as on the other side over here. And that basically means that this part is free to move along that cylinder. For our loads, you can see that we have two loads, two forces here set up on this structure. And the nice thing about it is that it kind of has this graphical representation with arrows to show where this load is located and what direction it's acting on the part. And if I open this up, you can see that we have we have this load in the x and the y direction with certain magnitudes that we've given it in the units of newtons. All right, so now that we have our structure and our constraints and loads set up, all we have to do to run the simulation is go up to the top left icon here and click on Simulate. So you can see within a matter of seconds, this thing is popping up results from our simulation. And it's important to note that this is a structural analysis. I know I mentioned that there's also modal, fluid, and thermal analyses, but we're going to be looking at a structural analysis today. So you can see that there's a window that popped up in the right-hand side here, and it realizes the von Mises stress that this whole structure is seeing. Now, if we're interested in seeing where the maximum and minimum points of stress are located on this part, we can click on this little icon in the bottom of this window, and it will highlight where these max and min points are. So the max point is highlighted in red here, and the minimum is highlighted in blue over here. Now, if we zoom in, we can kind of see that there's some spaces within this simulation. Um, so that's kind of like the background mesh that's running, right? And if we want to change that to have a more accurate result and get rid of some of these empty spaces, we can go up to the left-hand side here, click on Study and Performance Options. And here we have this scroll bar that you can basically change between speed and accuracy. So if I want this thing to be more accurate and maybe work a little bit slower, I can move it over to the right. And then if speed is my concern, I can go ahead and move that over to the left as well. For this demonstration, we're going to go and change this maybe a little bit more towards the accuracy side. Now you can see here that some of those empty spaces are removed, and we probably have a more accurate result here. All right, so what we're going to do now is we're going to go and make some design changes to this thing. We're going to change some of the geometries and see how that affects our performance of this part, with the overall goal of reducing the von Mises stress within this part. So the first thing I'm going to want to do is set up a simulation probe. So I click on this icon at the top here, and you can put this probe anywhere on the structure. But what I'm going to do, I'm interested in the maximum stress. So I'm going to click on maximum, and then the entity, I'm going to just pick this whole entire assembly. We'll go ahead and save that. And then in order to track the changes in stress as we make design changes, we can click on this query button and accumulate data. So now as we make design changes, we'll be able to see them graphically in this little window that pops up, and you'll be able to see the differences between stress as we make design changes. All right. So the first thing that we're going to do is we're going to change the geometry of these two bars here. We can see that our high stress point is right here, probably because of this weld and this circular surface here. So let's see what will happen if we change this surface to more of a flat surface. So what we're going to do is minimize our simulation tree. And that's the nice thing about CSL is that you can go right in between the model tree and the simulation tree. They're all located in the same place. It's just one unified environment, which is very nice. So I'll open up our sweep here, go into the sketch. And then, like I said, we're going to make this more of a rectangular profile. All right, that looks good. Now we can see this looks pretty good. We're going to click OK. And then what we're also going to do is change the geometry of this end here to also have more of a square profile. So I'll go into my swept blend. And I'll use this as my second section here to also have a more of a rectangular profile. All right, and then from here, to update this side, because this is a mirrored component, all we have to do is click on this icon at the bottom, regenerate. And just like that, we've made our first design change, and almost within, I don't know, a few seconds, we have our new results. So you can see we went from about 130 to around 57. megapascals of stress. And you can see that very clearly in this probe that we set up between our two design changes. So this is really nice if you're trying a bunch of different changes with your design or your structure. You can very easily see the difference between your two steps here. So let's go ahead and make another change. Let's try to maybe if I make this thing wider, it'll be more stable given the forces and constraints. So let's go ahead and change this from 132.5 to 135. Click regenerate. And then again, just look how quickly this updates here. It's super nice. We can go ahead and look at our probe here and see our step 3. So this is really nice because you can kind of tell if you're moving in the right direction, right? So as we move through our steps, we reduce the stress. As we made this wider, we actually increased the stress. So it kind of looks like we're moving in the wrong direction. So we can go ahead and change that back to what it was before. All right. So there's a few other really cool tools that you can use within CSL. Instead of kind of making educated guesses on how to reduce the stress of this structure here, we can run some analyses. So we can run sensitivity analyses and optimizations um, to make sure that we're getting the best possible geometry for our intended performance. Now, before I do this, we're going to say that one of our design requirements is circular top and bottom to this geometry. So I'll go ahead and change that over now. And again, we're just using some simple Creo parametric sketch and sweep functions here. And I've put in some predetermined sketches just to save time for this demonstration. All right. So now that we have our sketch based on our predetermined sketch, we can click OK. Everything looks good. And then again, we're going to change the end geometry as well to make sure this is a uniform geometry throughout. Hit OK. We'll hit regenerate to reflect those changes on the other side of the model. And we have our updated geometry and results. So let's leverage one of these analysis tools to make sure that we are optimizing this geometry here. We know that we need a round portion on the top and bottom of this profile. But what we can do is we can leverage these tools to make sure that we have the most optimum shape in terms of dimensions for this study. So we can click on sensitivity analysis up at the top here under design study. And basically what this is going to do is we can pick a dimension. We can then vary that dimension between a range, and we can plot the stress parameter and see within that range which dimensions are going to produce the least amount of stress. So I'll open up our sketch here, and today we're going to look at this 15 millimeter dimension here. and we're going to vary it from 12.5 to 15.5. We're only going to do 3 steps. This does take a little bit longer than just doing simple design changes, so for the purpose of time, I have to set my probe parameter, then we'll hit compute. This will take a minute to load here, but this is a really useful tool. When you have specific design requirements, you can vary those design requirements to make sure that you're producing the best geometry for what you're trying to accomplish with your design. And then you'll see the sensitivity plot accumulate the data points that we're calculating. And eventually it will come out with our solution here. So based on this sensitivity plot, we can see that within the range of dimensions that we picked, actually the best dimension in terms of reducing the amount of stress in the structure is this 15.5 dimension. So what we can do then is go over to our sketch, change this to 15.5, simulate that change, and we can see that our stress was actually reduced as this loads. It will pop up and show that the results of this study. Actually, it actually increased. It's probably because within the range that we chose within the steps, if we wanted to find that that optimum or the optimum dimension, we can go ahead and add more steps to that sensitivity analysis. One thing that we can also do, we know that we have a lower amount of stress around that 15.5 millimeter dimension, right? So what we can do is run an optimization on that dimension. It's pretty similar to the sensitivity analysis, but what we can do is we can set a goal. So our goal is to minimize the amount of stress within the structure, and we'll add our parameter of we want this stress to be less than what the current value is. We can hit OK here, and then we can add that same dimension back in here, this 15.5, and we're going to go from 14.5 to 16.5. So then we can go ahead and click compute. This optimization study does take a little bit longer. So what I've done is I've printed out these results already. So as you click compute, this optimization goal convergence graph will appear. After it loads for a second, it'll tell you how many iterations it took to converge on an answer. And then once you close this out, it'll ask you if you want to change your model as a result of this optimization. You can hit confirm, and then it'll automatically change that dimension for you, so that you know that you're at the optimum dimension in terms of what your performance goals are for your model. So that's all I had for this demonstration. I'm going to go ahead and go back to our slides and continue on. So I hope you saw what kind of value that CSL can provide from that demonstration. And really, it's a great tool. Going back to the start of this presentation, we showed you this design process workflow, right? And if you think about what are the most expensive portions of this workflow, and I would argue that it's probably this prototype and testing phase, right? So if we can incorporate simulation analysis in the empathize, define, and ideate blocks of this workflow, what we're going to do is we're going to reduce this cost and reduce this time to market for this workflow and really make it a much more efficient process. Along with that, you're going to be confident in your design, and you're going to have higher quality and performance, not only with your end design but also with your initial prototypes. Right? It really will help to streamline the process for you to find the most optimum product that you can possibly produce. Then along with this, you're going to have more confidence with new projects, right? If your company is looking to grow, looking to tackle on new new projects and new products, CSL is going to provide you with the confidence to be able to do that. So that is all I have for today. I really appreciate you listening in. If you have any questions about CSL or Creo or EAC in general,